All right, this is a continuation of Math 103, 11.4, using tree diagrams and the fundamental counting principle. So we're going to finish off this last section, and we are going to be making ID words and with repetition and without repetition. And we're going to see how that affects our counting principle and how many options we have. So we have the letters A, B, C, D, and E, and we're going to make a 4-letter ID card. So the first thing that I do is we recognize that we have 5 letters to choose from. But we're making a 4-letter ID card. So I'm going to put those blanks right there because each letter I'm going to be able to choose from is A, B, C, D, or E. And so the thing that I want to highlight here is that letters can be repeated in this first example. So that means that if I have a bag with those 5 letters in there and I reach into the bag and I pull out a letter, I have 5 letters to choose from for the first one. I write that letter down, but then I put it back in the bag. And so for the second letter, I have 5 choices to choose from. And the same with the third, and the same with the fourth. And we're always going to be multiplying those possibilities together to get our total number of choices. So I could have all A's, I could have 3 A's and a B, I could have 3 A's and a C, I could have 3 A's and a D, etc. So obviously we don't want to list those all out, but I have basically 5 to the 4th power, or 625 different ways that I can make a 4-letter ID card. Now, if I change it up a bit and I say, okay, this time a letter can only be used once, that's going to limit my number of ID cards can I make. So I have A, B, C, D, or E, and I'm going to write them. Okay, just going to write them down here. And so let's say for the first card, or for the first letter, I have 5 choices because I can choose any of those 5 letters. Well, let's say I pull out an A, and now I can't repeat the A, so I don't put it back in the bag, and so now I only have 4 choices. And let's say this time I pull out a D, and then I only have 3 choices. And then if I grab a B, then the last letter, I only have 2 choices. And again, we are going to multiply. And when I multiply those out, you can see that it drastically drops my number of possibilities to make that ID card when letters cannot be repeated. Okay? All right, so now we're going to look at something similar, but this time we have digits 1 through 5. So I'm going to write those digits. Okay, those are my choices, and I'm going to make a 3-digit code, so I'm going to have 3 blanks, and then I'm going to highlight that the digits can be repeated. So in this instance, I have 5 choices for the first one, 5 choices for the second one, and 5 choices for the third number. And so 5 to the 3rd power, or I have 125 ways to make a 3-digit code. Now I'm going to highlight they cannot be repeated. So when I create my blanks, I still am choosing 3 digits. And for the first one, I have 5 choices. But once I choose a number, so let's say this, I pick a number 1, then I only have 4 choices. Say I grab the number 3, and then I only have 3 choices. And so when I multiply those out, you can see it cuts it more than half of my original number. Okay? Now with telephone numbers, we've got digits. And so you got to remember that when we have digits, we have the numbers 0 through 9. So there are 10 total digits, single digits to choose from. And then that's what we're looking for. But we've got a phone number that's got 3 digits for the area code, 3 digits for the beginning part, and then 4 digits for the last part. And we have a few restrictions. This first blank of the area code and the first blank of the phone number cannot begin with a 0 or a 1. So that means that we have taken those choices out to be only 8 because we can't have a 0 or a 1. But then we have phone numbers that can be repetitive. So then the remainder of these choices, they have 10 possible digits that you can choose from. And we are, again, always multiplying these options together. So an easier way to write this, instead of having to multiply all of it out, is 8 to the second power, which is 64, and 10 to the 1, 2, 3, 4, 5, 6, 7, 8th power, which means 1 followed by 8 zeros, 4, 5, 6, 7, 8. And then when we multiply those together, I'm going to get 64 followed by 8 zeros. 5, 7, 8. So that makes there are 6,400,000,000 different phone numbers that you can choose, okay? All right, the last two examples are going to be similar to the ones that you're going to see in your homework. Now, you obviously are going to have to choose the correct tree diagram, but we're actually going to make it by hand, okay? So you've got this restaurant. It's got 3 choices of sandwiches, roast beef, ham, and turkey. It's got 2 choices for macaroni. 2 choices for salad, macaroni or potato. And then it's got 2 choices for drinks, coffee or soda. So if we're using the counting principle, 3 sandwich types, 2 salad types, and 2 drink types gives us a total of 12 possible lunch specials that we could order, okay? Now we're going to go ahead and make our tree diagram. So we've got 3 sandwiches. So we've got roast beef, ham, or turkey. And then off of each of these, we've got macaroni or potato. And then off of each of these, we got coffee or soda. And so we're going to do that for every sandwich. And then I'm actually going to list out my sample space so we can get a roast beef, macaroni, and coffee, a roast beef, macaroni, and soda, a roast beef, potato, and coffee, roast beef, potato, and soda. And then we move to the ham, macaroni, coffee, ham, macaroni, soda, ham, potato, coffee, ham, potato, soda, turkey, macaroni, coffee, turkey, macaroni, soda, turkey, potato, coffee, and turkey, potato, soda. So those are the 12 choices, and that's good to have them listed out because that's going to be the sample space. So this right here is all of my sample space, and then of course I have the tree diagram, and we're going to use that sample space to determine what is going to be the probability, okay? So now it says, what is the probability that the roast beef and a soda are selected, okay? So I'm going to highlight roast beef and soda, roast beef and soda. So it looks like we have 2 out of the 12 possible choices, which says we will have 1 out of 6 for the probability of a roast beef and soda, okay? Now, the next one we're going to do is what is the probability that neither macaroni nor coffee is selected? So anything that does not have an M or a C, okay? So that means I've got, let's see, M or a C. So actually I'm going to highlight this one. I can get a roast beef, potato, and soda. I could get a ham, potato, and soda. Or I could get a turkey, potato, and soda. So it looks like the probability is 3 out of 12, which simplifies to 1 out of 4. Okay? All right, and the last one that we have is this bag of marbles, and we are replacing it. That's important. So if we take out a marble, we can put it back and get the same color. And so using the counting principles, notice that we have 4 different colors. So using the counting principle to determine the number of sample points would be 4 for the first choice times 4 for the second choice, which makes a total of 16. Okay, now we're going to create that tree diagram. So we've got red, blue, green, and orange. And then off of each of these, we have another 4 colors: red, blue, green, and orange. And it's hard to make a diagram when you're so cramped in here, so that's why I'm going to have to come out here a little bit. Red, blue, green, and orange. And then last but not least, we have this one: red, blue, green, and orange. And so now I'm going to list the sample space. So we can have a red and then a red and a blue, a red followed by a green, a red and then an orange. And the first one can be blue, red, blue, 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 green, blue, orange. And then we go to green, red, green, blue, green, 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 orange. And then the last one is orange, red, orange, blue, orange, green, and orange, orange. So those are all of these 16 possible choices, okay? And then we're going to determine the probability of each of these instances. So for part C, the probability that a red ball is selected twice. So we only have one example out of the 16 possible choices where a red is selected twice, okay? Then we're going to find the probability that neither ball selected is an orange. So I'm going to put a little blue dot. Neither ball is an orange. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So it looks like we've got 9. Okay, so this is D. 9 out of 16. And that doesn't simplify, so that would be our answer. And then last but not least, we are going to choose the probability that an orange ball is selected at least once. And so you have to remember, if it's selected twice, it's still selected at least once. So I'm going to highlight where I have an orange ball selected at least once. So red and then orange, blue and then orange, green and then orange, and then all of these fit into that category. So part E, the probability of at least one orange is 7 out of 16. And that finishes 11.4 in Math 103.